Okay, let me start now. So I think this is where we left off, and we were watching this video about how the UPM is making biodiesel from tall oil. We're going to see tall oil again when we get to bioproducts, because there are a number of bioproducts that are manufactured from tall oil. We're almost done with biodiesel. So this slide says, as it says there, most of the biodiesel in this country is made from soybean oil. The reason for that is the two largest agricultural products in America are corn and soybean. And if you look at most junk food, if you'll read the label, you'll find that it's got either corn or soybeans in it, and they've all got, almost all of them have sugar in it. So maybe you can tell I'm kind of a health food nut. Anyway, soybean oil is very abundant in this country. And consequently, not very expensive. So we'll move
Professor?
on. Sure.
Sorry, I have a question. When produced biodiesel from soybean, the biodiesel is produced from the west or from the west of?
I don't think so. I think it's made from, so a lot of the, if you'll look at, again, if you'll go to the grocery and read the labels, you'll see that a lot of the protein is soy protein. If you go to the gym and they sell protein powder, a lot of their protein powders will be soy protein. So to get the protein, they separate it from the oil. So they take the seeds, they squeeze out the oil. All you have to do is press the seeds and you get the oil. And the protein remains then in the cake from the pressing. So soy protein there's not much protein in corn, right? And our two biggest commodities are corn and soy. So a lot of the protein, well, there's not a lot of protein in junk food, but a lot of it, what there is, comes from soy. And so the oil is left over. I wouldn't call it a waste product. I suppose you could call it a waste product, but it's sold, you know, it's sold if you'll, again, read your labels. A lot of salad dressing has soybean oil for the oil instead of olive oil, things like that. So soybean oil gets used, but yes, there's probably, I don't know the economics of the whole situation. I don't know if there's more soybean oil than there is a market for it, and biodiesel takes the leftovers. I just don't know. But it is the oil, and then the protein as you know, the big commodities that are produced from soybeans. So moving on from biodiesel to gasification. So gasification is a process where you take wood. It's similar to pyrolysis, and you've had the pyrolysis, hopefully you've seen the pyrolysis video. So it's similar to pyrolysis, except it takes place at a higher temperature, greater than 700 C, and it produces syngas. Syngas is sorry. I'm still not good at this. So syngas is hydrogen and carbon monoxide. So again, gasification is done in low or no oxygen atmospheres, and you can produce, then you get hydrogen and carbon monoxide from that. Using a catalyst, you can make hydrocarbons and also water. And I should have another arrow here because this reaction is reversible. It can go either way depending upon the catalyst and the conditions. So this is a way to go directly from biomass when you can take it at a high temperature and reduce and in the absence of oxygen to produce the hydrogen and the carbon monoxide. And so then the syngas is used. The Fischer-Tropsch process is the name for it. This couple of different chemists that came up with this many, many years ago. And so you can get these hydrocarbons. This is the general formula for hydrocarbons. And then down here you have the N number for this formula and the chemical name and the common name, right? So gasoline, jet fuel, and diesel fuel are all mixtures. And they're, but they're centered around they're mixtures of different N numbers, but the N number, usually the average N number is around 8, around 12, around 16. So you want to tune the process of gasification to make gasoline or jet fuel or diesel fuel or whatever. Sorry. This should be a video. Oh, maybe I need to.
The chemical conversion process uses heat to break down biomass into intermediates, such as gas or bio-oil, that can be upgraded into fuel and other products. One type of thermochemical conversion process is gasification, a method that uses heat to turn biomass into a hydrogen and carbon monoxide-rich gas called synthesis gas, or syngas. This in turn is converted into liquid transportation fuels or other products. Gasification occurs at relatively high temperatures. Here's one example of a gasification conversion process. Wood material, such as forest residue, is a common feedstock for the gasification process. For best results, feedstock wood chips are no more than 2 inches in size and have 20% to 30% moisture content by weight, depending on the gasifier. In the gasifier, the biomass is broken down into vapors in a carefully controlled environment that typically contains oxygen and/or steam. The syngas produced is made up of carbon monoxide and hydrogen. Char, a solid byproduct of gasification, is typically removed using a cyclone. Cyclonic separation allows removal of particulates from a gas stream without a filter by using rotational effects in combination with gravity to collect the particles. Tars and methane are also produced. Their quantity and composition depend on the gasification environment. Tars are high molecular weight organic compounds. If they are not removed, these tars will contaminate downstream equipment and inhibit fuel synthesis. One way to remove methane and tars is by using special catalysts to convert the compounds into additional syngas, thus eliminating the methane and tar problem while also improving the efficiency of the process. Additional cleaning and conditioning steps may be required to remove other contaminants such as ammonia, sulfur, and carbon dioxide. The syngas is then conditioned to produce the desired ratio of carbon monoxide and hydrogen to achieve optimal chemical reactions in subsequent steps. The pressurized hot syngas is then passed over a catalyst to form a liquid. The catalyst is contained in a reactor, and the syngas is passed through the reactor, where the carbon monoxide and hydrogen molecules combine to form larger molecules. These molecules are subsequently cooled, condensed, and refined into clean, renewable transportation fuels and other products. The Department of Energy has supported development of innovative technologies that result in higher yields and superior quality of biomass syngas. These efforts have also resulted in a much more thorough understanding of the gasification process. Enabled by these advancements, industry is deploying gasification technologies that will bring clean, renewable transportation fuels and other biomass-based products to the marketplace.
All right, that's gasification. Any questions?
A
Fairly.
gallon of gas.
What's that?
How much for a gallon of syngas? Is it more expensive than traditional?
Oh yeah, yeah. Way more. However, I think there are markets, and we have one of our former students is now he's the CTO for a company, and I think that's syngas is what they're making biofuels. So I think they're using gasification. All right. So yeah, it's more expensive. Well, when oil was $100 a barrel, no. And everybody was building gasification plants and pyrolysis plants and stuff. But now that oil is what? I don't know, in the teens or single digits or headed back up towards 40 to 50 to $60 a barrel.
Currently, it's at 81 cents a barrel.
81 cents, yeah. But that won't last. That's because people had contracts, right? So they were expecting a certain demand, and they had contracts to fill that demand, and then demand crashed. So the pipeline's full and with no place to go. So now you have huge oversupply. So once the contracts get in balance again, although that may be difficult with things bouncing around the way they are. Okay. Probably a good time to buy oil, actually. So pyrolysis. So the lectures are a little behind. So we should have done this before the lab, but we're going to do it now. So pyrolysis again is also done in this definition from the dictionary doesn't mention low oxygen environment, but typically it's done in a low oxygen environment, just like gasification. Although the videos did say that they do use oxygen, I don't believe that it's oxygen at 21% like it is in the atmosphere. It's a lower percentage. So pyrolysis is done around 500 degrees C. And I think we mentioned this, or I mentioned this in the lab video. And it's at the lower temperature, you get different reactions. And here's a video.
One type of thermochemical conversion process is pyrolysis, a method that uses heat to decompose biomass in the absence of oxygen.
Hang on. I want this to go full screen. I can't get to this. This stuff's in the way. There we go.
One type of thermochemical conversion process is pyrolysis, a method that uses heat to decompose biomass in the absence of oxygen. Here's one example of a pyrolysis conversion process. Wood material, such as forest residue, is a common feedstock for the pyrolysis process. For best results, feedstock particles are less than 2 millimeters in size and have less than 10% moisture content by weight. The process of pyrolysis heats the biomass at moderate temperatures in the absence of oxygen. This produces vapors that are condensed into liquid bio-oil. Char is also produced during the pyrolysis process. Cleanup and stabilization of the bio-oil make it more suitable for storage, downstream processing, and end use. Cleanup can consist of filtering out particulates and ash before the bio-oil is condensed into a liquid. Stabilization typically involves mild hydrotreating, a process that uses hydrogen to remove contaminants such as sulfur, nitrogen, or in the case of bio-oils, oxygen. Hydrotreating occurs with high hydrogen pressures in the presence of catalysts. Oxygen is eliminated mostly as water, along with some carbon dioxide. Other processes to remove oxygen are also being examined. Eliminating oxygen creates a less reactive bio-oil with lower acidity. The less reactive bio-oil may be stored longer and is more suitable for use as a fuel oil. The less acidic bio-oil may be more readily accepted into current infrastructure by achieving chemical compatibility with infrastructure materials such as pipes, reactors, and tanks. Mild hydrotreating is usually followed by more severe hydrotreating, which is required for the bio-oil to be suitable for use in a conventional petroleum refinery at several insertion points. Then, using technologies employed by existing refineries today, the bio-oil goes through a hydrocracking process, which tailors the molecule sizes to be in the desired range for gasoline, diesel, or jet fuel.
So you notice that there's not a whole lot of difference between the gasification and pyrolysis, except for the temperature, right? There is some, and the size of the particles, the moisture content of the wood is a little different. But the big difference is simply the temperature. And I want to make sure I'm still recording. Yeah, I'm still recording. Okay.
Professor, I have a question.
Yes.
If the difference is just the temperature, I can use the same equipment for pyrolysis and gasification, or are different?
A lot of it is the same, but not all. So you have with gasification, you're going directly from a solid to a gas. And you don't really have a liquid to deal with. You have particulates. And with gasification, I think also you don't need as much hydro treatment. With pyrolysis, you still get a lot of oxygen. With gasification, you're trying to go to syngas. And once you get to syngas, then the oxygen leaves as let me back up. The big problem with making biofuels out of wood is the oxygen in the wood. So because you don't want, if you have oxygen in a fuel, it's already partially burned, right? So this is the problem. And so getting rid of the oxygen, if you notice when we did the hydrocarbon there, the fuels we're interested in are hydrocarbons, gasoline, diesel, jet fuel. They're all hydrocarbons. They don't have oxygen in them. So getting rid of the oxygen is the big problem. And that's why they keep talking about hydrotreating, which means you add hydrogen. Of course, hydrogen is expensive. So you have to add, to meet the specs in the marketplace, to sell your biofuel for jet fuel or whatever, you need to add hydrogen. And you can see it right there, right? So pyrolysis, because it doesn't make syngas, it makes biochar and it makes bio-oil, and then you do have some gas that comes off, but not that much, not as much as in gasification. So in gasification, once you get to synfuel, and you use your proper catalyst, proper temperature, et cetera, you get rid of the oxygen, and that makes a much better fuel. With pyrolysis, the oxygen tends to hang out in the molecules. Excuse me. So it requires, in order to get to meet the specs, to make the fuel that you're interested, the biofuel that you're interested in, you have to add hydrogen or hydrotreat it, right? So at the same time, pyrolysis takes place at a lower temperature, so you don't have to use as much energy input to make and you get 3 different products, right? So you have a lower energy input because gasification, you've got to go all the way up. So yeah, you can burn what you produce to make the heat in gasification, but then you reduce your yield, and you've got capital cost and all that sort of stuff, and a lower yield is going to give you a higher cost. So all these things, the devil's in the details as usual. So how you set this thing up can make a big difference in whether or not you're successful as a company. Did that answer your question?
Yes, thank you.
Yeah.
I have a question about barbecue briquettes. Do they come from one of these 2 processes?
Yeah, it's kind of modified. I've got a slide on that later on for charcoal.
Okay, thank you.
Yeah. So pyrolysis of wood gives you 3 products, right? Gasification gives you 2. It gives you hydrocarbons and water. And with pyrolysis, you get 3 products. You get a solid product, a bio oil, and a gas. And these are typical values here. So it's not what we got in the lab in the video. We didn't get anything close to this. 450 kilograms of bio oil. I don't think we were close to that. Although you get to calculate it. So you can see, I'll read the lab reports and we'll see. Oh, and speaking of lab reports, I've graded homework number 1, and later today it's going to get posted. I still need to, I don't like grading online on the computer, so I printed everything out, and now I need to scan it all back in, and I'll email it to you, and it's also going to be in your mailbox, so you have something to look forward to when you come back finally for real, and there will be papers in your mailbox. Okay. So there's different versions of pyrolysis also. So this one is fast pyrolysis, and it has a different kind of reactor that's called a rotating cone. And with fast pyrolysis, you can increase the amount of bio oil, right? 60 to 75. Here it's 45%. Starting with 1,000 kilograms, you get 450. So here you can increase the amount of bio oil, which is really what we're after in this is liquid biofuels. So one of the disadvantages of, one of the disadvantages of solar energy is you need an electric car, right, in order to replace the energy required for transportation. So there's a lot of automobiles and trucks and buses on the road right now that are not electric. And so they use liquid fuels. Liquid fuels, hydrocarbons especially, have more energy density, a higher energy density than almost anything else that can be used for transportation. People have looked at a lot of different things, but if you look at the energy density of a battery, and then you look at the energy density of a gasoline engine and the gas tank, how much the gas tank weighs and how much energy you can get out of it, batteries aren't even close, right? batteries are getting better every year, but they're still not where they need to be to just be a drop-in replacement. So most of the electric vehicles are, they work, they're good, but they're being, people are using them for mostly environmental reasons. And also the electric vehicles generally cost more, but the operating cost is less. So that's one of the big advantages of electric vehicles. That's kind of off subject, but yeah, there are Teslas that have 500,000 miles on them and they're working like a charm. And you think about it, electric vehicles, they got no transmission, they got no valves to go out to fail. You've got no air filter, so the maintenance is way, way, way less on electric vehicles than it is on gasoline-powered vehicles. So anyway, fast pyrolysis is another option. There's a lot of different variations on this. There's been a ton of research done on this. The government has supported this for many years now. Millions and millions of dollars have been spent on research for a variety of, for gasification, pyrolysis, various ways to turn biomass into liquid fuels. So liquid fuels is what we're really after, because there's still, for quite a while still, there's going to be a big, I think, most people think, that a large part of the transportation fleet will require liquid fuels to run. So how do we get away from petroleum? We try to make liquid fuels out of biomass. Torrefied wood is another way to make energy. And here we're getting closer to charcoal, right? So you have you take the wood and you basically make charcoal out of it. And it can be a replacement for coal. And in fact, this is happening. The Ochoco Lumber Company is building a facility in John Day, Oregon, in the high desert. And the customer is Portland Gas and Electric, with their plants in Boardman. And this is their last year, I believe, unless something has changed. I think 2020 was their last year to run on coal. They have to switch to something else. They're going to switch to natural gas for most of their fuel, but for load leveling, because when people turn on their air conditioners in Portland, they need to increase the amount of electricity coming out of the Boardman plant. So for extra energy, they're going to use this torrefied wood, because it is a drop-in replacement for coal. So, and it's more expensive than natural gas, so that's why they're not using it as a replacement for coal. It's a replacement for coal in terms of energy, but it's not really, or in terms of processability, but it's not really a replacement in terms of price. And so natural gas is a better option in terms of price, but not environmentally, although short term, we've got a ton of natural gas. And then this is kind of just for fun. This is what some students in Sweden did. So wood pyrolysis was used as a fuel for autos, on-board fuel for autos. So these students decided to do the same thing.
Sorry, Professor.
Yes.
We are still looking at your slide.
Oh, you're not seeing the video?
No.
Okay. Well, this one is just mostly for fun anyway, so so you can watch it on your own, right? Because it's on the slides are on Canvas. Apologize for my skill set. So here's how Eric, here's how you make charcoal, and everybody else. Here's how you make charcoal. So yeah, it's kind of pyrolysis, but it's nothing like the advanced high-tech way to make pyrolysis to make the three products, right? So you just have low temperature, or sorry, low oxygen environment, and you have rotating plates here, and then the charcoal can come out the bottom, and you have so this is one way you make charcoal. You can also make charcoal or biochar. There's a variety of different ways to do it, and 100, 200 years ago, I guess now, actually making charcoal was a high-tech endeavor, and people would, technical specialists would take large pieces of wood, timbers type sizes, and stack them just right. So, and they had different sizes in different places, and they made a big pile out of the wood, made a bonfire. And the wood was stacked in the bonfire so that there was a low oxygen environment in the middle of the stack. So they would burn the stack, and it took constant care to keep moving the wood around, to keep everything, to maximize the yield of charcoal in the middle. And this was both high tech and also highly dangerous, right? So it was lost some people doing that. But in the very old days, that's how they made charcoal, and you can still do it today if you want. You can also just burn wood in a 55-gallon drum and put the lid on part way and poke a few air holes in the bottom so that you get reduced. The whole idea is just to reduce the oxygen content so it doesn't burn all the way. Right? So charcoal is another biofuel. And then there's this, which this has been a little while now, and I haven't heard anything more from folks. So I don't know what is this thing is being commercialized or not, but they have claimed that they have a one pot. So they take this little thing is the reactor, and then this is the gauge, right? So it shows you how tiny the reactor is. The reactor's down here, and this is the lid, right? And they've got a special catalyst that they came up with, and so they can go directly from biomass to hexane, pentane, and cyclic hydrocarbons. So liquid alkanes, so they can go directly from wood, put it in the reactor, open the reactor, and you've got liquid fuel. So that's quite a breakthrough if it's cost effective. The catalyst here, platinum, niobium, is expensive. Phosphorus is oxygen or not. So the platinum and the niobium, especially if they don't last very long, will be a big hang up in commercializing this. But if they can get it commercialized, it would be a huge breakthrough, wouldn't it? Okay. So much for bioenergy. Let's move on to bioproducts. Any final questions on bioenergy?
I have one question. Is the hydrogen energy density the same as fossil or hydrocarbon, or is it higher?
Say that again.
I said, is hydrogen gas energy density higher than hydrocarbon? Like using hydrogen as a fuel?
Yes, on a weight basis. The problem with hydrogen as a fuel is it's a gas. And to make a liquid takes a very low temperature, too low to be commercially feasible. So you have to pressurize it. And so, yeah, on a weight for weight basis, yes, hydrogen has a higher energy density than hydrocarbons. However, there's a lot of issues with how you handle the hydrogen as a fuel. So material handling is what's killed the hydrogen fuel. A lot of people have worked on it. A lot of people have come up with some very creative ideas, and a lot of people still believe in it. Another issue with hydrogen is when it burns, you can't see the flames. So you don't know if it's burning or not, which can be a problem. And if you have hydrogen under very high pressure and you have a crash and it breaks the high pressure hydrogen tank, then you can have a big problem too. So it's not really the chemistry of hydrogen fuel that stops it. It's the mechanics of actually making it happen on a commercial scale.
All right, thank you.
Okay, you bet. So bioproducts. So there's a concept called the biorefinery concept, and it's kind of morphed, you know, but it started as being analogous to crude oil. So you have the carbon sources here, and they go through a refinery, and you make a variety of different products. So this is the same concept as crude oil. So if the carbon source here was crude oil, it would go through a petroleum refinery, and you would make a bunch of different products. So the biorefinery is just analogous to the crude oil refinery. Right? And then the idea here is you start with renewable materials. Your products that you make all eventually emit CO2. The CO2 goes back to trees, plants, whatever, and goes back to carbon sources. So it's a closed loop. And these days, you're going to see more discussion, not so much a biorefinery, although I hear that once in a while. But now I hear more, the term I hear more now is the circular economy. So nothing escapes. It's the basic idea. And I don't know if you're going to be able to see this. So can you see a map of the world? Or do you just see the slide?
No, just a blank slide with bio-based chemicals.
Yeah. That's too bad. Anyway, this is a link to a map of a website that has a map of the world with different sites for different bio-based chemicals, and it tells you what the chemicals are and the company that's making them. So it's a nice reference if you're looking for some background information. Okay, so the first thing here so these are a variety of different bio-based chemicals. And we'll discuss a few of these, not all, right? So, and there's many others besides just these. These are just the ones I thought of basically off the top of my head. So this is a video. This is using tall oil not for biodiesel, but for chemicals.
Let us begin with an overview of the pine chemicals which we are working on. The word pine, of course, comes from the pine tree, and chemicals refers to the various products made using chemical processes. Pine chemicals refers to the chemical products derived from pine trees through chemical process. The pine tree, like other trees, performs photosynthesis, a process by which solar energy transforms carbon dioxide and water into the oxygen we humans and other life depend on for survival. At the same time, pine trees absorb water and nutrients through their roots, subsequently growing and synthesizing cellulose, a fiber material, and chemical substances. A stable supply of sunlight and water, coupled with constant plantation, will ensure that this natural chemical factory never runs out, making the pine tree a truly remarkable, renewable resource. So what kind of chemical substances can we obtain from a pine tree? Distillation of crude gum, which is a viscose liquid exuding from the incisions of the pine tree, can produce rosin, a resin, and turpentine, a solvent. Although turpentine has been used for oil paintings, it was also widely used as a solvent for paints before the appearance of petrochemical-based products. The pine tree contains fatty acids in the form of oil. The tall oil fatty acids indicated in the diagram are classified as fatty acids obtained from the pine tree. Tall, in this case, means pine in Swedish. Harima processes these substances into intermediate chemical products utilized by various industrial fields. 3 methods are employed to extract pine chemicals from the pine tree. The oldest and most well-known technique is to collect exuded crude gum by tapping live pine trees and then separating it into gum rosin and turpentine by distillation. The second method involves extracting wood rosin from pine stumps using solvent. The third method is the distillation of tall oil, which is a byproduct of the pulp-making process. Distilling tall oil produces tall oil rosin and tall oil fatty acids. Rosin and fatty acids have a wide range of applications. For printing inks, rosin is used to uniformly adhere pigments to paper and other substrates. In the paint industry, fatty acids are used as raw materials for manufacturing alkyd resins. Resin is also an essential component of soldering paste. And for synthetic rubbers such as tires, rosin is used as an emulsifier for manufacturing styrene butadiene rubber.
So that narrator obviously wasn't a chemist. When she said styrene butadiene, she meant styrene butadiene, or SBR rubber, which almost all tires are made out of. Some tires still have natural rubber in them, and I think tires have different kinds of rubber in different parts of the tire. So natural rubber is still used for tires, but probably the largest chemical that's used or polymer that's used for tires is SBR. Okay, so that's a little more information about tall oil and why it's called tall oil, right? So here's some information on, and if you're following along, I haven't, I just found this slide and I haven't changed this PowerPoint. Canvas, so if you're following along with your slides, you don't have this one, but you will. I'll get this done after So, three different kinds of biopolymers, right? You can have polymers directly extracted from natural materials: starch, cellulose, cellulose derivatives, cotton, etc. Chitosan, which comes from shrimp shells, lobster shells, things like that. And pectins, right? So pectins come from plants. They're basically well, in terms of, they're similar but not the same as hemicellulose, right? So then you can have, those are the polysaccharides. Then you can have proteins, right? Casein comes from milk. Collagen comes from connective tissue in animals. And I think gelatin does also. And then you have plant proteins, wheat gluten, and various other kinds of plant proteins that are biopolymers. You can also have bio-derived monomers, which is the way you make polylactic acid, and there are other polyesters that are made from bio-derived monomers. So you get the monomer from the, does everybody know what I'm talking about when I say monomer and polymer? If you don't, please let me say something.
Me.
Okay. Okay. So we're going to talk about this when we get into adhesion. We'll cover it in more depth. A polymer means many parts, right? So poly means many and mer means part. So a polymer is basically a molecule that has a unit that repeats, and it can repeat thousands of times. So that repeating unit is called a monomer. So mono means one, right? So monomer is one part, polymer is many parts. So the monomers are what connect together to make the polymer. So does that help, Tiana?
Yeah, that helps. Thank you.
Okay. So we have, then the third type is polymers produced by microorganisms and bacteria. So polyhydroxyalkanoates, those are produced primarily by algae, I believe. And bacterial cellulose is produced by bacteria. And bacterial cellulose is really cool. If you want to look it up online, it's called kombucha leather, because kombucha tea, hopefully everybody knows what kombucha tea is. Kombucha tea is actually made using bacterial cellulose. When you make the tea, you put a SCOBY in, right, to your mixture, and it makes the tea. So you have tea and sugar, and you put in a SCOBY. The SCOBY is bacterial cellulose. And so the SCOBY grows, and it also will have symbiotic yeast with it, and it will give you that tangy flavor of kombucha. And the yeast will produce a gas too. So this is a kind of a general overview of the different kinds of biopolymers that can be produced as a class of bioproducts. The largest volume biopolymer today in terms of market presence is polylactic acid, or PLA. It's made from corn. You can also make it from sugar beets. You can make it from a variety of things. You just need sugar to start with. And you ferment it, and so you ferment it not to ethanol, but to lactic acid. So that's generally anaerobic fermentation to get lactic acid instead of aerobic to get ethanol. And then from the lactic acid itself can be used to make PLA, but you don't get a high molecular weight polymer, so you don't get good properties. The polymer, higher molecular weight, the higher the molecular weight the polymer has, generally the better the properties, up to a point, of course. Right? And so if you then convert it to lactide, which is this process here. So this is the formula for lactic acid. And if you'll look at this closely, you'll see that what you have here is an anhydride. So you have CH3, and if you put water in here, you could put an H here, and you could put an H here, or an OH here instead of O, and you would have the lactic acid, right? So you have the carboxylic acid, C double bond O, COH, C double bond O, C double bond O, and if you put a hydrogen here, it would be OH, right? And then here's the CH3, there's the CH3. They don't show the hydrogen in this thing, which is typical. And then you have O, if you put an H here, you would have OH. Right? So what you're doing is losing water. And the way you make an anhydride is you take two acids and you remove water and you get an anhydride. So if you make this anhydride, now you can do a thing called ring opening polymerization, where this anhydride, you see it's a circle or circular or cyclic, and it just opens up. It flips open and you get this polyester, right? So then this is the PLA. So this is the formula for PLA. Okay. So that's how you make it. And you can make, let's see, so in terms of traditional, how PLA compares to traditional plastics. So here's PLA on this end. This is PET, number 1, polypropylene, number 5, styrofoam. So in terms of emissions, you see it's much lower. In terms of energy, it's a little bit lower. In terms of water, it's kind of in the ballpark, except for making styrofoam. So it does have these advantages. Plus, it doesn't come from petroleum. That's the important thing. And it was one of the first that was developed. It went big. Well, it went big, and then it kind of went, there was a lot of money that was invested, and it was invested by Dow and Cargill originally. And they spent a ton of money getting this thing off the ground and didn't really make much money. The market didn't really explode like they were hoping it would. And then it got bought out, and I think it's one or the other of them, I forget which one now, bought the other one out. They renamed it NatureWorks, so now it's NatureWorks, and it's a big deal. And there are other companies now that make PLA, and it's available worldwide. And there are plants in various places around the world that make PLA. It's not just, it was invented, I guess you could say, in America, but now it's available worldwide. And you can get it as solid plastic, you can get it as films, you can get it as foam. There's a lot of different products that you can make out of PLA. It's not like polypropylene. It doesn't have the greatest properties, so there's been a lot of research done on how to improve the properties of PLA. One of the biggest properties is if you make a plastic spoon out of PLA and you stir your coffee with it, the spoon will melt, or it will bend at least. And so raising what's called the heat deflection temperature of PLA, so that you can use it for utensils, plastic utensils with hot food, has been a big source of, and there are ways to do it. Doing it the least expensive way is still active area of pursuit. And then this is a really interesting one. So this one has BASF behind it, and Avantium. A bio replacement for PET. PET is number 1. It's water bottles, it's soda bottles, kinds of containers are made out of PET. And this one's going to be called PEF. So still, you need ethylene glycol, but you also start with furans, and furans can be obtained from biomass in a variety of different ways. They're in biomass to start with, so you can just extract them, but you can also, through processing biomass in a variety of different ways, you can end up with furans, and you can then make furan dicarboxylic acid. So and what they're claiming is PEF is actually better than PET for food and drink packaging because it has superior barrier properties. So it looks like this. So they've got but I think it's more expensive. And they've got the plant, and the plant is running, but I don't think it's running very hard because they're having trouble. People aren't willing to pay more yet for a greener product for these applications. So this was another interesting biopolymer developed by Fraunhofer in Germany, and they call it Arboform. And so they make speakers out of it. So they make, and you can make bowls on Arbofill. And what they did was they found a way to just turn wood into plastic. And you can also blend it with other plastics, right? So they have a process that simply turns wood into plastic. And the lignin, I think, is the plasticizer. And I got a sample of this, and no, I don't have a sample of it. That's right. I tried and failed. And but looking at the specifications for it, it is pretty brittle compared to other polymers. So it's not like a replacement for polyethylene or polypropylene because it's really brittle. So I think it has limited applications in the marketplace, and it's not going to be the panacea that we wish it was, right? So then this is...
Professor,
yeah.
do you think that there would be room for these markets if we stopped subsidizing oil and subsidize these instead?
I would hope so. Depends on the subsidy, right? So the stop subsidizing oils, it sounds like a great idea. But I'm just one person. I'm not speaking as a professor there.
I can't hear you, Professor.
Oh, sorry. The subsidizing oil seems kind of crazy to me when it's at 81 cents. So although it's getting subsidized, it's getting bailed out, right? And I don't know that anybody's bailing out Arboform or bailing out any kind of biofuel. There's smaller markets, there's smaller presence in the marketplace, I should say. So hopefully someday, all right? Hopefully someday that'll happen. So this is a thermoplastic made from lignin. I'll define thermoplastic later on when we get to adhesion. And so what this is that this is the head of a 3D printer. So this is a object made out of lignin that's been 3D printed. And they claim that the lignin is I think the lignin is, so it's this green line, and this purple line, right? So HIPS is high impact polystyrene, and it's just polystyrene with little tiny few micron sized rubber balls in it. And then you have the, come on. So you have, then these other lines are, so this is HIPS, and these other lines are the lignin-based plastic. So you can see the difference. This is viscosity versus shear rate. So you have a rubber, you can make a rubbery polymer out of lignin, and you can 3D print with it.
Professor, do you know how you can print with the polymer of lignin if it's thermoplastic? Because it's supposed that plastic you can't melt. So.
No, thermosets you can't melt. Thermoplastics you can.
Yes.
And this
Yes.
is, I think it's just filament printing. They just make a filament and then put it through a regular 3D print. I don't know if the temperature is different. I don't know the details on it. So it's also, it can be a shape discovery material, right? Thermoresponsive. So you can deform it and then you heat it up a little bit and it's recovered. So this is 50% lignin, and doesn't say what the other stuff is. It's a invention, it's a patent, etc. It could be a secret. And let's see if this will play. ORNL is Oak Ridge National Lab. Okay. So all kinds of interesting science going on these days with bioproducts and biopolymers. This is from 2004, so it's really old now, but it's still good information. So DOE's Department of Energy, PNNL is Pacific Northwest National Lab. It's in Richland, Washington, about a 5-hour drive from here. NREL is a National Renewable Energy Lab. It's in Golden, Colorado. And the Office of Biomass Laboratory, I don't know where that is. So they started out with 300 building blocks of bio-based chemicals, right? And then they narrowed that down to 30, and then they narrowed the 30 down to 12. And they figured out that, not considering price, right, those 12 can technically substitute for most of the chemicals that we get from petroleum. So we can replace, technically, it is technically possible to replace petroleum with bio-based chemicals. It's not being done because petroleum's cheaper, but technically it is possible to do. So that's the technical aspects of the problem are not what is stopping us. And then this gives you just a, this is a really busy slide, and I don't really want you to read it right now, and you can really don't have to read it at all. For this class, I just put it on here so you might want to refer to it in the future if you ever get involved in any of these areas. It kind of gives you an overview of various products and um, different types of biomass that can be used to make biochemicals and biomaterials, really. Right? So this one is making carbon fiber out of the lignin, which has been an ongoing project for, I don't know, maybe 15 years. And ORNL, Oak Ridge National Lab, has been heavily involved in this, at the University of Tennessee, plus a whole bunch of other people. So you take, you don't try and do it from cellulose and hemicellulose, too much oxygen. Try and take it from lignin and try and make carbon fiber. And what they're trying to do is make carbon fiber that can be used in carbon fiber epoxy composites for automotive. Automotive is, well, you'll see it in the next slide, why they're doing automotive. And I don't know that we're going to be able to see this one. Nope, you can't see it. You'll have to read it yourself, or see it yourself. So this little video is just about making carbon nanofibers based on biomass. It's short, and the work's being done at UBC, just up the road in Vancouver, BC. Okay. So
Professor?
Yeah.
It is possible use the lignin that is produced in the craft process to make paper. For example, extract this lignin and use in this project?
Yes, that's what people are doing. So, you know, the lignin has value to the pulp mill because it's their energy source. And if they didn't burn the lignin in the recovery furnace, then they would have to purchase energy from somewhere else. So it's not that the lignin that's produced today in pulp mills has no value, but it has the value of its contained energy. So if you can find a product that you can make from lignin that is more valuable than the energy value in the lignin, then the pulp mill will be happy to sell you the lignin, and they can replace the energy with other natural gas or whatever. Right? So it's making higher value products out of lignin that is the challenge. And yes, that's exactly what all these different lignin polymers and things, that's what they're doing. The expert on this in our department is Glenn Lee. Well, he's in our department and other departments. He's got a lab up in food science, and but he's an expert on biorefinery and lignin. He developed a course on 573 on bioenergy and bioproducts. And as I mentioned, if you want to do a deep dive into this whole thing, take that course. It's now being taught by Jerry Presley, our new biodeterioration person. And so, but before that, it was taught by Glenn. And Glenn's still around. He's teaching other courses in other departments and things. So on this chart, you've got fiber modulus, and on the y-axis, you have tensile strength, okay? So we're looking at mechanical properties here. And this shows you the different types of carbon fiber and what they cost. It's a 2013 data, so it's a bit dated. And but it also shows you their performance, right? So tennis rackets, bicycles, wind towers, they use carbon fiber that costs about $10 a pound. And then when you get into aerospace, they use carbon fiber that's much more expensive, and space stuff is aerospace, heavy on the space part, can use carbon fiber that's up to $80 a pound. So you want you get higher materials, but you get higher performance, but it costs you more. The main thing that you're doing to get the higher performance is reducing the defects, right? A bunch of you are engineers, so hopefully you get that. Reduce the defects, you increase the performance. Where the Oak Ridge National Lab lignin is right now is here. So not even close to even the lowest of the commercial applications. The best they've done is here, but not all that repeatable, right? So this is 2013, it's been a while, and I asked one of the fellows that's involved in this, I said, are you really going to be able to get up to automotive? Because that's really where they want to be, is they're shooting for the lowest one, which is automotive, but it's a big market, right? So it will be a big market for lignin. And I said, are you really going to get up there? And he said, yeah, we're going to make it. To my knowledge, they haven't made it yet. So this has been an ongoing thing for maybe 20 years. I think they really need a breakthrough that they haven't had so far. However, the market for carbon fiber is predicted to increase rapidly. If we could get carbon fiber, so these are the two different ways to make carbon fiber right now. Polyacrylonitrile, PAN stands for polyacrylonitrile. It's a synthetic polymer, comes from petroleum. And then pitch is actually a biomaterial, right? It's pitch. But it's a tiny part of the market because it doesn't give you the high value properties. So the PAN is what gives you the carbon fiber that's highly crystalline and also low defects. And so it's growing rapidly. And if we could get a lower price for carbon fiber, we'd make a lot more things out of carbon fiber epoxy composites because it's a wonderful material. It can replace steel and it's lighter weight than steel. So you could use it in a whole lot of places if you can get the price down, right? And if you could come up with an inexpensive way to make carbon fiber out of lignin, you could basically explode the market. Plus, there's not that much PAN around, right? So if this really, then we're up here now, but if the carbon fiber market keeps growing, going to run out of carbon fiber. So the price is going to go up and then people do other things, make it out of steel. So, so we really could use, technologically, we could really use a low cost but high quality source of carbon fiber. So you might see this on, I've seen it in one or two places. So the USDA does certify whether or not a product is bio-based, and they certify both the product and the package. Right? So that can give you, as a consumer, can tell you if you're buying a bio-based product. And then finally, you can see here that if you want to give us more biomass for things like chemicals and fuel, then eat less meat because the biggest use for agricultural biomass is animal feed. So I'm not a vegetarian, so don't get any ideas that I'm getting on my soapbox. It's just, this surprised me when I first saw it, so I thought I'd show it to you. And we've got 4 minutes left. Next, the next subject is adhesion. So I'll just say a few words about it. What we're going to do here in this topic is answer these questions, right? So we're getting ready to study composites and how they're made. And so this is CLT is included. And so we want to CLT and other composites, so OSB, plywood, particle board, MDF, they're all glued. So we want to learn what the glue is, right? Why we use glue, why is it sticky, and then what cover polymers, right? Because almost all of the glues, to my knowledge, all of the glues that are used for wood products are polymers, or contain polymers at least. And then which polymers are used for wood composites? We're just going to look at the big ones, the ones that have the largest presence in the marketplace, because there's that's a whole class. I mean, we could do a whole course on adhesion and polymers for adhesion. So, and let me show you this, because this is just for fun. So this is a application of adhesion. Okay, so you saw that, and this statue is made by a Chinese artist, and it's made from 30,000 pieces of paper glued together. And that's why he can pull it apart like an accordion there. So it's just a fun example of adhesion. And I think that's probably a good place to stop. We'll start next time here, look at advantages and disadvantages, and move along at the different theories of adhesion. I just managed to get the PowerPoint up this morning, so sorry about that. I should have had it up sooner, but it's up now. So you can have a look at the slides if you wish. And we will continue our discussion on Thursday. So thank you, everyone. And let me know. Yeah.
Can I ask a question about the homework?
Yeah.
Could you just give a little direction on problem 2? Because I'm not really sure where I'm supposed to start. Or like how to.
Problem two is for the comparing solar panels and burning firewood.
Yeah.
Yeah, so the idea there is to just look at, yeah, actually when I was looking at that, I kind of left out a piece of that problem. So the idea is to just compare energy and compare it on as kind of just a first approximation basis. So you just take the cost of the panel, not the cost of installing it, the wiring, the inverter, and all that stuff. Just the cost of the panel and how expensive it is compared to the cost of Douglas fir Douglas fir firewood, which is about $200 a cord. So in terms of energy, which one would be better? Now, you can take the problem a little deeper if you wish. It's like, how many years would it take for you to, because the solar panels should have at least a 20-year life. And how many years would it take for you to break even if you compare, if it takes you 1 cord of plywood to get through the winter and versus that same amount of energy in a solar panel. So you can feel free to critique that question because there's a lot of issues involved and a lot of details omitted. So you can talk about things like fireplaces aren't efficient, right? You're burning wood for energy and you're burning it in your fireplace, because the solar panels are for residential, they're from Home Depot, right? So burning wood in your fireplace actually uses energy, it doesn't create energy. stuff like that. So you can take it as far as you want to go. And you can look up the cost of the Douglas fir and compare it on a cost basis, right? And then get that break-even number. So.
Awesome. Thank you. That's really helpful.
Yeah. Okay. All right. Anything else?
Is there a replacement for polypropylene and polyethylene high density that's bioplastic? In performance, at least?
No, there's not a drop-in replacement. But there's, but for example, when the university reopens, if you go to Dixon, or any of the other, I think any of the other food courts on campus, and you get a drink in a cup, the cup will be made out of PLA. If it's a cold drink, it'll be made out of PLA. And that's replacing cups typically made out of polypropylene, right? Or PET. So it depends on there's not a polymer, there's not a biopolymer that's a drop-in replacement for all the different applications for polyethylene or polypropylene, or PET. But there are specific applications where they have figured out ways that it makes sense. And they've been pretty successful. There's a local company, it's called Ecknow Tech, is the name of it. It used to be here in Corvallis. They moved to, it's actually between Corvallis and Albany on Highway 34. And they're growing like gangbusters. They're doing really great business. And that's exactly what they're doing, is replacing petroleum products with bio-based products and figuring out which products and how to make it work with using bio-based materials. So.
What was the name of the company?
Ecknow Tech, E-C-N-O-W, E-C-N-O-W-T-E-C-H, Ecknow Tech. And the owner of the company is a good friend and has been working here. We've done work for many years together, and he's a good friend of the university. And in fact, he's looking to hire some engineers as interns this summer. So, and I think the chemical engineering department is going to supply him with some interns. And he's had interns before from OSU. So yeah, it's a growing business. It's a good business to get into. And it's, again, what you're fighting is the low costs of petrochemicals and petroleum polymers. But there's a huge, as I said in the first lecture, we're riding an enormous wave of sustainability, and it's worldwide, and pretty much everybody's on it. And so almost every day, Ecknow Tech gets calls from companies saying, can you make XYZ out of biopolymer and help me be more sustainable? Because that's what customers are demanding. So as long as us customers keep demanding bio-based materials, you're going to see more and more of them. That's the way it works.
All right, thank you.
You bet. Anything else? Very good. Then have a good day, and I will see you on Thursday. And the composites lab, which is Thursday's lab, is up on YouTube now. So it's on my channel on YouTube. So if you want to watch that, you can. I'll get the data sheets up today. You'll need data sheets to write your report. They'll get up today or tomorrow. So.
Thank you, Professor.
Okay.
Thank you, Professor.
I'll see you Thursday. Take care. Bye-bye.
Good day, Professor. Bye.
Thank you,
Bye-bye.
Professor.